So now I will talk about the choice of good hash function. So what is a good hash function? I want to remind you of a very important assumption we made before the assumption, which is again we called we basically talked about when we are mapping elements to the hash table, we would like for the elements to be equally likely to fall in any of the M slots. Okay, this is what we call the simple uniform hashing. Simple uniform hashing. Again, and all it says is that each key is equally likely to hash to any of the M slots. Okay? Independent of what's there, what has been hashed, what hasn't been hashed, and all of that. Okay? So this is a very important, very powerful assumption because again it allows the keys to distribute uniformly across the table. And the size of the lists when we have collisions is not going to be very large. Okay, we are not going to have that worst case scenario where one slot in the hash table has a very long list. Okay, so a good, one criterion, okay, not the criterion, but one criterion of a good hash function is that the function itself is that the function satisfies as much as possible this assumption. Okay, the function satisfies as much as possible the simple uniform hashing assumption. Why do I write as much as possible? I mean, in general, it's impossible to verify. In general, in practice, it's impossible. In most cases, it's impossible to verify whether a hash function satisfies the assumption. Okay? And the reason for this is because we usually don't have knowledge about the probability distribution from which the keys are drawn. Okay, so I don't know much about where these values are coming from. Okay, so in practice, it's almost, again, it is impossible to verify whether a hash function satisfies the assumption. So this is why, I say we would like for it to satisfy the assumption as much as possible, so to be as close to uniform distribution as possible. And there are heuristic functions that have been designed and work well in practice. There are no theoretical guarantees in them, in the sense that nobody has proved theorems about them in terms of the distribution and so on. But they are heuristic functions, and one of them is what we call the division function. So one of them is the division method. So we divide the key by some value, and the other one is the multiplication method, where we multiply the key by some value. Okay, but before I talk about division and the multiplication, I want to actually pause for a second and talk about this notion of keys and what it is that we hash. Very often, the keys that we try to hash are not really numbers. Okay, so we like numbers. So imagine that the universe of the keys was all the natural numbers. Okay, then we can perform operations on numbers. We can multiply, we can divide numbers, and so on. But what if I'm trying to hash strings? Okay, what if I want to hash the string A, B, B, A? Okay, or what if I'm dealing with computer program and I want to hash, the keyword while? Okay, then these are not numbers. What can I do? do I deal with them, and what happens in this case? Well, the nice thing is that we can turn every string into a number. So imagine that we have, and throughout this lecture, I will assume that we are dealing with some set of characters. Okay, so suppose that, and since we deal with computer programs, let's talk about the ASCII code set or character set. Okay, ASCII character set. So this is the set of all the letters from A to Z, lowercase, uppercase, all the digits 0 to 9. Also all the special symbols, underscore and plus and minus and so on. Usually, in many cases, the cardinality of this is 128. It has 128 characters, and sometimes you can have 256 as well. Okay, so we can imagine now that our alphabet is all the way from 0 to, again, if I assume 128, from 0 to 127. Okay, so now if you give me a string W from this alphabet, okay, W and sigma star, it means this is a string whose letters are one of these ASCII codes 0 through 127. Now I can interpret this as a number as follows. I can actually take, so let's assume first the length of W is P, so that we stick with some value here. So I can take the value K of that string as the sum of Wi times R to the I, where I equals 0 to P minus 1. And in this case here, R would be the size of this. So for example, in our case, R would be 128. Okay, so this would be, let me fix this here. This is P minus 1. Okay, so we basically are taking every letter in the string as a number in that ASCII code, and we multiply it by R to the I, where I is the radix of character code. So here we call R the radix of character code. Okay, so now we have this notion of a string is basically a number. We can turn it into a number. And now, since a string is a number, I can basically think about just dealing with keys that are numbers. So now I can go back to U being, let's say, the set of natural numbers. Okay, so what is the division method? The division method, by the division method, h of k is k mod m. This is all it says. That take the key, divide it by m, and return the remainder. Okay, so just to remind you that, so suppose k is 19 and m, let's say, is 7, then h of 19 is 19 mod 7, which basically says divide 19 by 7 and take the remainder. If I divide 19 by 7, then we have 5. Okay, this is the remainder. So h of 19 would be 5. So I'm mapping 19 to the key 5. And now the big issue is, what do we choose m to be? Okay, so really the question with the division method, what value of m should we use? Okay, so here, imagine that I take m to be r. Okay, so suppose m, let me use a different color here, blue. So suppose that I take m to be r. Okay, r which appeared before r equal to 128, let's say. So what happens here is that if I take k, remember that k is this sum Wi times r to the I equals 0 to the p minus 1. What happens if you divide a number of this form? What happens if I take this k and take it mod r? If I take hk to be k mod r, what do I get? It's basically the very last character of w. The very last digit of W, WP minus 1, sorry, here, okay? So this is the last character of W, or of the key, okay? And is this good or bad? Okay, so what I am saying here is that imagine that you give me a set, please listen carefully to this. Imagine you give me a set of words, you know, W1, W2, all the way to WN. So these are the keys that we want to hash, okay? And all I'm telling you is that I will hash all these words to for every word here, I'm gonna hash it to a key whose value is the very last character in W1. Because remember, W1 are made of these ASCII codes between 0 and 127, okay? So if W, you know, W1, let's erase this. If, let's say, last character of what I mean by last character is the rightmost one or the least significant bit of this string. So last character of W1, let's say it is, you know, the code 92, let's say. Then H of W1 is going to be 92. And suppose the last character of W2 is 41. Then H of W2 is 41, okay? So the only thing we do here is that, you know, you give me a string, I take the least significant bit in it, or the last letter in it, and I say this is your key, or this is the slot in which it's gonna hash. Now, is this good or bad? It depends. We cannot say this is bad. If the strings are distributed uniformly by their last character, this is a great function. I repeat, if all 128 characters in the alphabet are distributed uniformly as last characters in all the keys that we are trying to hash, then this is a perfect function because we end up having uniform distribution. However, this is very hard to see in practice. You know, if you look at a computer program and you think about the keywords, for example, in a computer program, not all ASCII characters appear in keywords. In fact, keywords usually don't have digits or the symbols plus or something like that. So this is a bad function. Okay, this is a bad choice of M. Okay, so M equal R is bad. Can I take M equal R squared? Well, if I take M equal R squared, the division function, the only thing it gives me is that H of K, now instead of the last character, it becomes just the last two characters. K mod R squared is basically the last two characters. WP minus 2, WP minus 1. I'm abusing notation a little bit here. I'm using W here and K. But again, keep in mind that K are these letters or digits in W. Okay? So again, if the last two digits are not distributed uniformly across all the keys we are trying to hash, then this is a bad choice of a hash function. Okay? So we don't want R, we don't want R squared, we don't want M to be even also, because if M is even, then H of K is odd or even, depending on whether the last character in W or in K is odd or even. Okay? We don't want that. So what M is good then? One of the safest choices that have been advocated here is that a safe choice for M, safe choice for M is prime. Okay? So you can take M to be prime. Now, we have to be careful. We have to be careful about it because there are so many prime numbers. There's an infinite number of prime numbers. We don't want M to be large either. So imagine M is equal to R minus 1 and it is prime. Imagine the R minus 1 is prime. Okay? This is a bad choice. Okay? So M equal R minus 1, and if R minus 1 happens to be prime, this is a bad choice. Why? Because now if I take this string here, Wi, R to the I equals 0 to P minus 1. And I take this mod M, which is M is R minus 1. What we get here is the W to the I, sorry, the R to the I actually disappears from here now, becomes like this, mod r minus 1, okay? What happens here? The r to the I disappeared. Why is this? Because of a simple mathematical result that we can say that r to the I mod r minus 1 is 1. Because of this, I get to this point. So what happens here? That you give me a key of this form, wi r to the I, the sum of these. And what happens here? I got the function mapped to something of the form wi. Wi, it means that r to the I is not there, so there is no weight to these characters. So imagine your w, imagine the w is that where the w0 is, let's say, 2, w1 is 4, and w2, let's say, is 0. So I'm talking about the string 2, 4, 0. So this one is going to be mapped to 2 plus 4 plus 0 mod r minus 1. But let's actually, so this is the string 240, but let's look at the string 402 now. What is it going to map to? It's going to map to 4 plus 0 plus 2 mod r minus 1. What about the string 024? It's going to map to 0 plus 2 plus 4 mod r minus 1. What is it that I'm trying to say here? Look at all these, they are all the same. So under this choice of key of m equal r minus 1, what we end up doing here is that all the strings, all the permutations of the same string end up mapping to exactly the same slot. Once again, is this good or bad? I don't know. It all depends on the probability distribution on the keys. If the permutations are distributed uniformly, then this is good. If the permutations are not distributed uniformly, or the choices of words are not distributed uniformly, this is not good. Okay? So m equal r minus 1, and r minus 1 is a prime number. Okay, this satisfies that safe choice of m being prime, but again, it's not a good one. So now, you might be asking, okay, I said that we should not choose r, we should not choose r squared, we should not choose an even number, we should not choose r minus 1. Okay, then what do we choose? Okay, so what do we choose is, one safe choice, or what the community recommends, is that we want m to be prime number that is not in the vicinity or the neighborhood of r plus minus a or r squared plus minus a for small values of a. Okay, so what we are saying here, again, remember that I said r minus 1 is not good, and if you take a to be 1, then r minus 1 is one of those. So look, here's r and here is r squared. What we are saying is that, draw some range around r. Okay, so these are all the numbers around r. Again, if a is up to 5, so for example, it would be r minus 1, r minus 2, r minus 3, r minus 4, r minus 5. r plus 1 plus 2 plus 3 plus 4 plus 5. The same thing here is the vicinity of r squared. What we are saying is that choose some prime number somewhere here or here or here. Okay, so don't choose a prime number that's close to r or to r squared. Okay, now one last word I want to say about this is, I want you to keep in mind that m should not be too large, because that defeats the whole purpose of doing a hash table, using a hash table. If m is 200 million, that's not a good hash table. We want m to be small. So if r squared, if r, for example, is 256, if we look at the ASCII code that has 256 letters, r squared is already a large number. Okay, this is relative for practical applications. R squared is a large number. So if r equals 256, all we need to do is just choose a prime number that's not too close to R. And it's been shown that in practice it would work. Okay, so to summarize here, the division method says we basically take k divided by m and take the remainder, and for the choice of m, let it be prime not close to R plus minus, or not close to R. Okay, not close to R, sorry, not close to R. What it means, not close to R, again, choose a small value a and just make sure that that prime number is smaller than R minus a or larger than R plus a. But again, it should not be too large because that's the value of m, and we don't want to create a huge table. Okay, because that defeats, once again, defeats the purpose of using hash table, and it might not be practical. Okay, so this is all there is about the division method. Is you take a number and divide it by m, take the remainder, take m to be a prime number not too close to R. The other method here, I'm not gonna actually elaborate the same amount of time on it. I will say it very, very briefly, very quickly, is that in the multiplication method for choosing, so if I wanna do multiplication for choosing a hashing function, again, the division method, we said we want m to be prime. What if we need to have m that's not prime? Okay, so in this case, we can do the following in the multiplication. H of k would be take k times a for some small number a. So a will be a small number between 0 and 1. Between 0 and 1. Multiply k by a. Subtract from it the floor of k times a. If you look at this carefully, what is k times a minus the floor of k minus a? Ka. This is just the fractional point, the fractional value of the number. So if you take, if Ka is 3 point, for example, if Ka, let's say it's 3.912, remember that the floor of Ka will be 3, and Ka minus floor of Ka will be 0.912. Okay, so it's just the fractional, this whole thing, Ka minus the floor of Ka is the fractional value of the number Ka. And we take this and multiply it by m. This is why it's called the multiplication method. Okay, so we multiply it here by m. And in this case here, there's two things that we need to talk about. M, what is m, and what is a? Okay, so m, it's been, again, and the two, I'm gonna make statement about both of them that have been shown to work well in practice. M can be, R to the L. Again, R is the radix of the character code. R to the L for some integer L. For some integer L. So you can take R to the 5th, for example. Again, but you don't want it to be large, okay? So if R is very, very big, 256, maybe you can take L to be 1, okay, or 2, but not much larger than this. A, here is a magic value for a. It's the square root of 5 minus 1 divided by 2, and this is some value that's close to 618, okay? Where does this come from? Again, this is a recommendation by a very famous computer scientist by the name of Donald Knuth, and this is not just a recommendation because he said, I think this is a fancy number that should work. This is based on practical analysis of different values of a. It's been shown that this value here would work well in practice for multiplication, for the multiplication method of choosing a hash function. Okay, so we talked about the division method where we divide k by m and take the remainder. For the multiplication method, we multiply k by some small constant a between 0 and 1. Then we take just the fractional value of that number and multiply it by m. One important thing I want to say here is that the a is a constant for this function. So we don't choose different a for different keys. Okay, so if I choose a to be 0.618, this is the same a that's going to apply to hashing all the elements there. Okay. The last word I want to say again is that both the division and the multiplication method seem to work well in practice. They are heuristics. There is no theorem and proof that says they actually satisfy the simple uniform hashing assumption. But theoretically, we can design different type of function that can guarantee this kind of distribution. We can prove theorems about it, and that's what we're going to talk about next.